Module 2, Lesson 13, Relationships between two numerical variables. I can determine if a scatter plot has a linear, quadratic, or exponential relationship. And I can use a scatter plot or an equation to make predictions about other data points. Open your workbook to page 71. Not all relationships between two numerical values are linear. There are many situations where the pattern in a scatter plot would be best described by a curve. Two types of functions are often used in modeling non-linear relationships are quadratic and exponential functions. Okay, so we've been talking a little bit about relationships having a curve, and now specifically we're going to talk about quadratic and exponential curve. Okay, example 1, modeling relationships. Sometimes the pattern in a scatter plot looks like the graph of a quadratic function, with the points falling roughly in the shape of a U that open up or down as the graph below. Okay, so when you see a U shape, this is what we call a quadratic function. And that's a U shape. In other situations, the pattern of the scatter plot might look like the graph of an exponential function that either have an upward slope or a downward slope. So in this case, these two graphs here are what we call an exponential function. And this one is also. You'll notice this one is curved up, and this one is curved down. Okay, so those are exponential functions, and the other one is a U curve. Now it's called a quadratic function. Let's revisit the data on elevation. In feet above sea level, the mean number of clear days per year. The scatter plot, this was example 1 from yesterday. The scatter plot of this data is shown below. The plot also shows a straight line that can be used to model the relationship between the elevation and the mean number of clear days. The equation is a line. Y equals 83.6 plus 0.008x. There's the equation of this, and we're used to writing it more like this. Y equals 0.008x plus 83.6, where this is the M and this is the B. And they wrote it a little backwards. And they probably obtained that equation from a graphing calculator. Number 3, assuming that the 14 cities used in the scatter plot are representative of cities across the United States, should you see more clear days per year in Los Angeles, which is near sea level, or in Denver, which is known as the Mile High City? Justify your choice with the line showing the relationship between the elevation and number of clear days. Okay, so in this case, this has a positive slope. So it's a positive slope. That's saying as elevation increases, the number of clear days is increasing. So Los Angeles has the elevation, let's see, Los Angeles here, the elevation is near the sea level, whereas Denver is known as the Mile High City. And a mile high is more like over 5,000 feet. Okay, so Los Angeles is near sea level, closer to 0, whereas Denver is a mile high, closer to 5,000. It says, the question was asking us, would you see more clear days per year in Los Angeles, or would you see more clear days in Denver? And according to this, we're saying with the positive slope, the higher the elevation, the more clear days. So with that said, Denver would have more clear days than Los Angeles. And then they said justify your choice with the line showing the relationship. So first of all, I'm saying Denver would have more clear days based on the positive slope or correlation. Meaning the higher the elevation, the more clear days. Now, in terms of looking at the line, it says justify your choice with a line showing the relationship between elevation and mean number of clear days. According to this, if Los Angeles is at sea level is, let's say right here, 0, that means that Los Angeles might have an average of 75 clear days. And Denver, that's about 5,280, going straight up from about there. That would put Denver maybe right around here, just using my line as an approximation. And that's looking like it's around close to 125 clear days. So just using the line as an approximation, the line says that Denver, okay, so using the line, Los Angeles, LA equals 75 clear days. And Denver equals 125. Okay, that's how you use the line to make predictions. Okay, it says use one of the cities, number 4, one of the cities in the data set is Albany, New York, which has an elevation of 275 feet. If you did not know the mean number of clear days for Albany, what would you predict this number to be based on the line that describes the relationship between the elevation and the clear days? Okay, so what we want to do for that, Albany has an elevation of 275, so we want to approximate where that would be. So 500 would be in the middle. 275, well, 250 is approximately halfway to 500. So 275 is going to be a little bit past the 250 mark. So I'm going to guess this point right here would maybe be Albany. So I'm guessing Albany is a little bit under 75. Let's see. It says, if you did not know the mean number of clear days for Albany, so I mean, let's not go back and look at the table, what would you predict this number be to be based on? Oh, based on the line, sorry. Not based on the point. Based on the line. Not based on the points. Based on the line, so that means that I would go up to here to the line. Not put a red dot there because that makes it a little confusing. So based on the line, so maybe right here, I would predict it to be a little higher than 75, maybe around 80. Approximately 80 days. Another way that we could find that out would be to actually use the equation. So putting in my calculator and say y equals, because the equation is also the line, 0.008 times times 275 plus 83.6. And I'll plug that into my calculator and see what I get. Let's see if I come out close to 80. 0.008 times 275 plus 83.6. And I got 85.8, so it is pretty close to what I guessed on my line. So about 86 days, really. Okay, another city in the data is Albuquerque, New York, and it has an elevation of 5,311 feet. If you did not know, so here's Albuquerque. If you did not know that the mean number of days for Albuquerque, so not looking at the table, what would you predict this number to be based on the line? So I'm going to use the equation again for that, just because it's a little bit more accurate than looking at the line. So y equals 0.008 times 5,311 plus 83.6. I'll plug that in my calculator. 0.008 times 5,311 plus 83.6. And that one's coming out to 126.08. So technically, when we're talking about days, you don't really need to use the decimal. It's approximately 126 days. What's the prediction of the mean number of clear days, number 6? Based on the line closer or closer to the actual value for Albany, which actually was 69, or for Albuquerque, which was 167. How can you tell this from looking at the scatter plot? Okay, so for let's see which one was closer. So for Albany, the actual number was 69, and the calculated answer came out to 85, I think, 86 days. So that means that the calculated answer was off by, I'm going to do 86 minus 69. So it was off by off by 17 days. Let's find out for Albuquerque. So again, the actual, in this case, was 167, and the calculated answer using the equation is 126 days. So to find out how much it was off by, I'm gonna take 167 minus 126. We'll find out which one was more accurate. This one was off by 41 days. So it was more accurate for this one. Okay, so it says, what's the question? How can you, okay, so now it asks us, how can we actually tell that the prediction was closer for Albany versus, so if we look at this, go back to the graph here. So first of all, this is going to be the point. So here's the point that I looked at. Here's Albany. And here's the point that I looked at. Look at the difference there. Versus here's Albuquerque, the point that I plotted, versus this point here. This is Albuquerque's point. If you look at the difference between the point I plotted versus the point that the actual point, look at the difference in those line segments that I just drew. The Albuquerque line segment is a whole lot longer, which is telling us that the line is going to actually be a lot more off for Albuquerque than it is for the other one? Oh, Albany. So the closer that the points are to the line, to the scatter plot, the better that the scatter plot, or the scatter plot line is going to be, the line of best fit, I'm sorry, is going to be at predicting the actual answers. Okay, let's look at a quadratic model. It says farmers sometimes use fertilizer to increase crop yield, but often wonder just how much fertilizer they should use. The data shown in the scatter plot below are from a study of the effect of fertilizer on a yield of corn. Now, a minute ago I just said let's look at the quadratic model, because that's the title of this section, quadratic model. How did I know this was a quadratic model as opposed to a line? You guys see the curve? So looking at these points here, notice that it's curving, and it's in that U shape. And that U shape, it's just an upside down U. That U shape is what makes a quadratic model. Okay, so exercise 7, it says the researchers who conducted this study decided to use a quadratic curve to describe the relationship between the yield and the amount of fertilizer. Explain why they made this choice. And I just kind of answered that. Because the point made an upside down U shape. Okay, the model, number 8, the model the researchers used to describe the relationship is y equals 4.7 plus 0.05x minus 0.0001x squared. Okay, every time it's a quadratic model, you're going to see an x squared, where x represents the amount of fertilizer for every 10,000 square meters, and y represents the corn yield, how much corn that they were going to be able to grow.
per 10,000 square meters. Use the quadratic model
to complete the following table.
Okay, so we're going to plug in these numbers for our x values. So for example, for the first one, I'm going to plug in my calculator, 4.7 plus 0.05 times 0 minus 0.0001 times 0 squared. And you should get just 4.7. It's multiplying by 0. Multiplying by 0 is just going to cancel out. So that part goes away, and that part goes away. You're left with just the 4.7. Okay, now you guys should be doing this with me and trying it. Make sure you understand how to put in your calculator these numbers with the x squared. So for the next one, you're going to change the 0 into 100. So 4.7 plus 0.05, and now I'm changing these to 100. 0.0001 times 100 squared. Notice my square is outside of my parentheses. Okay, for this one I'm going to get, let's see. You should be trying this also, making sure you're getting the same answer. And if you're not, you should be calling me over to ask me why. I got 8.7. Now, technically, these numbers are in 10,000 square meters, so that's really 8.7 times 10,000, or excuse me, times 10,000. So y represents, or milligrams per 10,000 square meters. Okay, so now the next time around, I'm going to change this to 200. And I'm getting 10.7. Then I'm going to change it to 300. I got the same number again. Interesting. It is correct. Now I'm changing to 400. There's actually a reason why that comes out to be the same. This one comes out to 8.7. And you'll notice that these two numbers come out to be the same. And if I did 500, it would actually come out to 4.7. And again, there's a reason for that. Okay, based on this quadratic model, how much fertilizer should be used for per 10,000 square meters would you recommend that a farmer use on his cornfield in order to maximize his crop? Justify your answer. Okay. So to maximize his crop, The maximum is actually going to be right in the middle of the 200 and 300, which would be at 250. So let's find out what we get when we plug in 250. And the reason I know that is because right in the middle, because of the pattern of the points when they are starting to repeat again. And so the middle is going to be right in the center of where they start to repeat again. So let's try that number and see what we get. And here's why, here, let me draw a picture so I can explain why I know that better. So what's happening, the maximum of this is going to be the maximum right here. The high point. So what's happening is on each side of the high point, you get in the same numbers. So like right here and right here are going to be the same. So that's like the 10.7, 10.7, and then it starts to go down a little bit, 8.7, 8.7, and then 4.7, 4.7. That's what's happening. So right here in the middle would be the maximum, which is apparently at the 250, halfway between the 200 and 300 that gave the 10.7s. Okay, so plugging in 4.7 plus 0.05 times 250 minus 0.001 times 250 squared. Very interesting. This is coming out to negative 45.3. Thought I was doing something wrong because I did it twice. And I put my answer. Oh, there we go. I was doing something wrong. It's coming out to 10.95. That's making more sense. There we go. 10.95. Okay, so based on the quadratic model, how much fertilizer should we use? So this would be it. And would you recommend the farmer use on his cornfields in order to maximize this crop? So it would be 10.95. Let me get the milligrams per 10,000 square meters. Per 10,000. What was it? Square meters. Okay, and now let's look at an exponential model. It says, how do you tell how old a lobster is? This question is important to biologists, to those who regulate lobster trafficking, and those who regulate lobster trafficking. To answer this question, researchers recorded data on the shell length of 27 lobsters.
that were raised in the laboratory and whose ages were known.
Okay, so we're looking at, well, first of all, this one, can you see why this one's an exponential model? Which is probably one of the questions. Because this one's got that curve that swoops upward. Okay, so number 10 says the researchers who conducted this study decided to use an exponential curve to decide the relationship between age and exterior shell length. Okay, so we got on the x-axis, exterior shell length, and we have age on the y-axis.
Explain why they made this choice.
So I just answered that one. Because the points curve upward from right to left. Okay, the model that the researchers used to describe this relationship, next question, is y equals, this is how exponential models look. 10 raised to the negative 0.403 plus 0.0063x, where x represents the exterior shell length and y represents the age. The curve below is shown on the scatter plot below. Does this model provide a good description in the relationship between age? So there's the graph. It's kind of how I drew it. Between the age and the exterior shell length, why or why not? And I would say yes, it does, because the curve is going through the center of the points. On your last quiz, I saw some of you trying to connect dots. Again, you were not trying to connect the dots. Even when we did the linear graphs, you were not supposed to connect the dots. Your line was supposed to go through the center of the dots. And the curves are supposed to go through the center of the dots. So yes, this does look like it is a good description. And why or why not? Because the curve is going through the center of the dots. I'll leave it at that. Okay, based on the exponential model, what age is the lobster with an exterior shell of 100 meters? So we're going to be plugging in 100 for x. So y equals 10 raised to the negative 0.403 plus 0.0063 times x, which is 100. Okay, a couple different ways that you can plug that into your calculator. So first of all, turn mine on. Okay, there we go. So in this calculator, I can put 10 and then raised to, and then in that box, I can actually type everything that it says, or I could have figured out what it equals, what this part of it actually equals first, and then put that answer in. That would be the other way to put it in the calculator. Okay, but I can type everything in this particular calculator as it says right there. So negative, oops, right on my calculator. Okay, negative 0.403 plus 0.0063 times 100. And my parentheses equals. Okay, so there's the answer I got. And so that came out to y equals 1.686, and y stood for the age, I think in years. Yes, age in years. So a little over 1.5 years old. Okay, suppose that trapping regulation requires that any lobster with an exterior shell length less than 75 millimeters or more than 150 millimeters must be released. Based on the exponential model, what are the ages of lobsters with exterior shell lengths of 75 millimeters? So that means I want to plug in 75. So y equals 10 raised to the negative 0.403 plus 0.0063 times 75. I want to find out what the ages of those lobsters are. And what are the ages of the lobsters with shell lengths that are greater than 150? So then I want to do the same problem again, but I want to plug in 150. So that I can find out what ages I'm allowed to keep. Because if being smaller than the answer I get for the first one, or bigger than the answer I get for the second one, I have to put it back. So I'm going to kind of cheat here so I can do this kind of quickly. Right, got my calculator down. You can go back up and grab a problem, and then kind of scroll back, and I'm going to change this part that's in parentheses. That's kind of one of the advantages of plugging something in parentheses. You can see what part you want to change. So this age, the first age is 1.17. So anything less than 1.17 years or greater than, so I'm going to go back again. Oops, get my calculator again. Or greater than, I'm going to change that into 150. 3.48, almost 3.5 years. I have to put back. Okay, so basically anything less than a year or anything more than 3.5 years, I'm going to have to throw back. So any lobsters. Okay. And that's today's lesson.